Hello and welcome to this webinar on lab processing and analysis of multi-increment soil or sediment samples. My name is John Peard of the Hawaii Department of Health Hazard Evaluation and Emergency Response Office, or commonly called the HERE office. I wanted to mention first that the slides that we promised to put up, a copy of the slides that we promised to put up yesterday, we had a glitch on that, but they are posted now, so you can access a copy of the slides from our HERE webinar page, and that information was provided to you earlier. So I wanted to provide just a few introductory remarks before Diane Anderson of the Agricultural and Priority Pollutants Labs presents this webinar. I will also join in at the end of Diane's presentation to help answer any questions. This webinar follows a series of 4 webinars provided by the HERE office in June on decision unit multi-increment sampling investigation methods that are used for site assessments and decision making by the state of Hawaii and are detailed in our online technical guidance manual. Those previous webinars as well as related presentations can be viewed from links on our HERE office website or the HERE office YouTube channel. The HERE office has been using DU-MIS investigation methods for soil or sediment contamination assessments since 2007 and first provided technical guidance on these methods for environmental consultants working in the state in 2008. We have periodically updated this guidance based on experience gained over time. From early on, training has been a key component of implementing DU-MIS guidance in Hawaii. Over the years, we have utilized or recommended Chuck Ramsey of Envirostat Incorporated to provide the core training on multi-increment sampling to our staff, environmental consultants, and laboratory personnel working in the state. In addition, our technical guidance, as well as our webinar series more recently, provide details and examples for implementing the DU-MIS sampling approach for conducting investigations and making decisions. Our technical guidance on laboratory processing of multi-increment samples is found in Section 4 of the HERE Office Technical Guidance Manual, and as you will hear, is a critical part of the overall DU-MIS investigation methodology. Because many of the soil samples collected in Hawaii are now analyzed by labs on the mainland, good one-on-one communication as well as careful review of lab SOPs on their processing and analysis methods for MI samples is very important to the performance and completion of soil or sediment contamination investigations that meet or exceed our state's guidance. Diane Anderson is technical director of one of the mainland labs that is providing DU-MI sample support for consultants working in our state, and I'm pleased to hand you over to her now for this webinar presentation. Diane, are you there?
Yes, I am. And thank you very much, John. I really appreciate this opportunity. Our legal name is Agriculture and Priority Pollutant Laboratories, but we're doing business as APPL Inc. We've been around for 35 years, and we hold accreditation for ISO 17025, DOD 5.1, and NELAC. We also have certifications in 10 states. We were on the Office of Solid Waste Methods Development contract as a subcontractor for 17 years. During that time, we had the privilege of working on the multi-increment sample methodology developed in method 8330B with Barry Lesnick, Alan Hewitt, Chuck Ramsey, and Marianne and Michael Walsh. All but Alan have done an on-site visit, and we even have Chuck's nod of approval. We have used MIS in at least 24 states, and of course Hawaii. We have also used MIS in several foreign countries. We've run it for explosives, including perchlorate and picric acid, metals, pesticides, dioxins, and volatiles, using various combinations and permutations of MIS. Roughly a third of our work is MIS. Multi-increment sampling is a comprehensive sampling methodology used to represent a specific population or decision unit and provide a foundation for defensible decision making. Once the samples arrive at the lab must use the same principles in sample processing, or the field efforts to reduce error can be severely compromised. Typically, the greatest proportion of overall sampling error is expected to be associated with field sample collection and/or field sample processing methods. These errors can be minimized using G's sampling theory in the field. However, errors attributed to incorrect lab sampling of bulk samples, of subsampling of bulk samples, can also be very significant and in fact could be orders of magnitude. So correct lab processing of MI samples is also critical. It's important to realize that sampling theory applies to both the field and the lab. All lab personnel using this method must be trained in MIS sampling theory prior to performing MIS. The staff needs to understand the basic concepts along with the sources of measurement error and the basis of G's theory in order to perform MIS properly. G's theory deals with the estimation, prediction, and minimization of the variance of sampling errors. Understand that there are many ways to subsample in the laboratory, and proper training is the only way to ensure that it is done properly. The main reason to use MIS is to reduce error due to sample heterogeneity. This allows us to produce sample data where the mean is less uncertain and is closer to the true value. This is done by using science, what a concept, making the data more defensible. MIS saves cost in the lab by reducing the number of samples needed. And when we refer to the unreliability of discrete sampling, we're generally talking about field sample collection. But the same is true for lab subsampling, making discrete sample results unreliable, and the level of concentration in discrete samples is generally underestimated. Discrete sample processing begins by scooping a small portion of the soil off the top of the container and weighing it. This method does not compensate for sample heterogeneity, even if the sample is stirred first. Stirring causes the finer particles to settle to the bottom, which increases the heterogeneity. And the EPA methods do not require enough sample mass to overcome fundamental error. For example, the metals method requires just 1 gram of sample. For VOCs, 5 grams are required, and for most of the other organic analysis, between 10 and 20 grams of sample. This is what a typical discrete sample looks like. The small amount of soil in the plastic digestion vessel is all that is required to be run for the EPA metals method. The definition of correct sampling procedure occurs when every particle in the sample has the same probability of being selected for the subsample. 1 gram of this sample, grabbed from the top of the jar, is obviously not representative. Results from a laboratory duplicate taken in this fashion would likely not be reproducible. It would also be difficult to extrapolate back to the field and determine what the results represent. Stirring a bulk sample in a container would not only increase heterogeneity, as finer particles would go to the bottom, but taking a single or even replicate samples just from the surface of the container would be expected to significantly underestimate contamination for contaminants like metals, where higher concentrations are typically associated with the smaller particles. Now, this is a picture of a 2-dimensional Japanese slab cake. This is an MIS sample, and the entire sample is used in the sampling process. A minimum of 30 increments is used, The more increments you use, the better, just like in the field. The increments are all the same size. They're collected with the proper tool to ensure that the increments go all the way to the bottom of the sample. So we basically mimic what happens in the field. So what am I looking for? Well, I want data that represents my entire sample. The entire field MI sample that is collected and submitted is processed during the MIS sample preparation, but only a small portion of a discrete sample is processed. On the left-hand side in the plastic container is 1 gram to be run for metals. It's necessary to have the proper equipment to perform the sampling processes for MIS. A variety of equipment is necessary, including large trays, bakery racks, balances for large samples, a variety of 12-inch sieves, temperature and humidity controlled room, plenty of hood space, as well as table space to process large sample volumes. The sampling tools are important also. A square scoop is designed to get to the bottom of the sample so that all particle sizes are included in the increments taken. It's important to collect a representative sample, which includes all of the fines that are on the bottom of the foil. This is especially true for samples that are not ground because they have more particle size variation. A coring device, like the bottom half of the slide, can be used when the sample is ground, since there is less particle size variation. Make sure that the tool you are using is of the proper size to collect the target amount of mass after a minimum of 30 increments are taken, because all increments need to be the same size. This can take some practice. Subsampling in this manner attempts to select a subsample that is representative of the bulk sample. That is, to capture the similar range of particle sizes, shapes, and associated contaminant concentrations in the lab subsample as occur in the bulk field MI sample. Taking replicates, if you take a sample and take a replicate of it, you in essence take a triplicate from different systematic random locations across the entire spread out sample, will provide documentation whether the subsampling was reasonably representative or not. We use the %RSD to make that determination. These representative lab subsampling procedures are designed to follow through on the correct procedures for reducing potential sampling analysis errors with the field MI samples. Ideally, this should also pertain to the discrete samples. References for subsampling MIS. Francis Pittard literally wrote the book on this using Pierre G's sampling theory. It's an excellent reference. An EPA method 8330B Appendix A, a guidance for obtaining representative laboratory analytical subsamples from particulate laboratory samples. The method itself only applies to explosives, but it is applicable to other classes of compounds as well. And there are detailed methods for field collection and/or field processing of MI samples that can be found in the HER Office Technical Guidance Manual that John mentioned in sections 3, 4, and 5. And in section 4 of that same guidance, it addresses lab processing issues for MI samples. Not on this slide is EPA method 3050B Appendix B. This is in the draft stage right now, and it specifically applies to metals. It's not been published yet, but I understand it's very close. There are multiple sources for MIS lab guidance, and they've been available for many years. Although they all describe MIS lab sample processing and subsampling methods, they do vary in detail. And there are particular issues with each that may be need to be closely scrutinized or perhaps modified based on your project DQOs, the laboratory's experience, and maybe recent information. To use MIS in the laboratory, you need to have a clear understanding of the data quality objectives. The DQOs, once established, do not change once the samples are sent to the lab. The DQOs are the same in the field as in the laboratory. The goal is to properly determine the representative average contaminant concentrations in the bulk samples submitted to the laboratory. This can be done in many ways, as you'll see, so communication with the lab is critical. MIS investigations result in significantly fewer bulk samples for analysis than discrete sampling methods, and only MIS methods are recommended for site evaluations in Hawaii. MI samples are large in mass, which impacts the laboratory in the handling and the processing time and associated costs. Replicate samples, which are triplicates, are collected for one or more decision units in the field, and during lab subsampling, commonly one per batch of 10, to evaluate the representativeness of the field as well as the laboratory procedures. Precision is determined through the calculation of the relative percent differences. Lab processing details will vary for different contaminant types or groups, and the final results are reported on a dry weight basis for comparison to environmental action levels. The decision unit must be defined and properly communicated to the laboratory, or there's no chance of the lab doing a proper job. There are lots of options to meet project objectives when using MIS. With discrete, there's only one option. Everyone needs to understand the correct MIS procedures that will be implemented both in the field and in the lab. Ideally, the lab would be brought in at the DQO stage, but this rarely happens. So please keep the lab in mind as you go through this process. This information is not new and just applicable to MIS, but it's needed for any sampling plan. Thought needs to be given to the analyte integrity, which will affect the analytes of concern. It needs to be taken in the field as well as in the lab. The list of analytes needs to be communicated well, along with the concentrations of concern. Can your reporting limits meet the action levels? Are there special handling requirements for any of the analytes? Will drying be a concern? Will preservation be needed? And if so, what type? Will the samples need to be cooled, or can they be at room temperature? All of this needs to be addressed. So what resources do you have available to you? Well, first and foremost is your regulator. Make sure you communicate with your regulator. Ask them questions until you thoroughly understand what they want. Then coordinate closely with the lab to ensure your sampling plan goals and quality assurance criteria are clear. Review the laboratory standard operating procedure for sample processing to ensure that it meets expectations for your samples, and specify in writing any variations or adjustments that you require. The lab can be a good resource for you too. Ask them questions. They can help you determine the type of sample processing you need for your analytes. Ask them for their standard operating procedures and read it. Ask them what type of QC they perform and how frequently. And ask for references that relate to your project. And it's always a good time, when budgets and time allow, to schedule an on-site visit to trust but verify. Once you've verified that you have the right lab, and ideally this was done during the DQO process, you should now have the confidence to trust that they know what they are doing. Now you can use them as a true resource. The lab should be able to answer your questions. They will have the knowledge to ask you questions and be able to explain the entire process to you, including if and how your samples will be affected. They'll tell you if your samples need preservation and what type, and they can guide you in the proper selection and for containers, and can demonstrate how your samples are processed entirely through the process. And we actually do this through the use of photographs. So what particle size do I need? Well, the way your data will be used is going to determine how the sample is processed. Soil is generally defined as less than 2 micron particle size. If you're looking to use the soil portion of the sample for your analysis, make sure that you use the entire portion minus only the particles greater than 2 millimeters. You're going to hear me say this over and over today. Samples are typically air dried before sieving for the non-volatile contaminants. Some semi-volatile contaminants may be prone to loss if air dried before sieving and subsampling if the source is a fresh one. Therefore, samples for certain semi-volatile contaminants may need to be wet sieved or analyzed wet without drying or sieving, and these measures need to be considered when looking at how to process your sample. If you're looking to establish bioavailability, you'll need to clarify the particle size you need. It's important to remember, if you're using a smaller portion, for instance, 150 micron portion for the bioavailability, you need to process the entire portion of sample in that particle size that you're looking. So you want to use only the particle sizes that are this big to begin with. You don't want to grind, and you want to make sure that you use a large enough sample mass to reduce the fundamental error to an acceptable level for the analytical method that you're going to be performing. Mechanical grinding using a puck mill reduces particle size which increases the subsampling precision. This is especially critical for samples that have nuggets of concentration in them. Particle size. What size do I want to use? Well, maybe you want to look at the bioavailability of, say, arsenic and lead, but you may want to also look at PAHs in the whole soil. Well, you can separate the less than 150 micron portion, run the arsenic and the lead, and recombine the entire sample and process it as if it were a regular soil, going through all the steps necessary, and then analyze the PAHs. If you're looking at lead in a range where nuggets are suspected, and you're looking at the entire soil fraction, grinding is the best way to get a representative sample. Now, the bowl the lab uses in the grinder will contribute metals to the final results. So if it's a stainless steel bowl, chromium could be a problem. You're going to want to check with the laboratory and see how much of a contribution they get from their bowls. They will have this information available. And in a lot of cases, the CRQLs are high enough that the contribution from the bowl won't bother the final analysis. But all of this needs to be communicated and decided up front. Particle size separation is quite easy to do. This is a list of the different sieve sizes available, and it tells you what the particle sizes you'll get. The ones that are highlighted are the typical particle size sieves that we use in our laboratory. To process soil at 2 millimeters, the entire sample, less pebbles and sticks, is sieved through a number 10 sieve. Now, according to EPA method 8330B, care must be exercised not to eliminate soil agglomerates during this step. This is critical for clay soils. The most moist soil can be broken into small pieces with a gloved hand or other instrument. So it's important to process the entire sample. You also want to make sure that when you sieve the sample that you don't force particles through the sieve. One, it'll damage your sieve, and two, you'll have greater than 2 millimeter material that you're sampling. A mortar and pestle can be used to disaggregate clumps of soil that remain on the screen. And it may be important to save or examine the greater than 2 millimeter portion of the sample if there's a potential maybe for contamination of interest remaining, such as lead pellets, for an investigation of a former shooting range, or maybe large paint chips and samples collected around building foundations. In our laboratory, we typically keep the 2 millimeter portion in a Ziploc bag with the sieved portion, so it can be examined at a later date if necessary. The MIS options in the laboratory, there are literally hundreds of different ways. No matter how you process the sample, subsampling is equally important and must be defined. And if you're going to dry, sieve, grind, not dry, not sieve, not grind, the subsampling is very, very important. These are project specific, and your lab must perform them correctly, or your samples won't meet your project goals. This is a typical 1 to 2 kilogram sample that comes in a Ziploc bag. Now, sometimes receiving a Ziploc bag that looks just like this is the first clue we have to the fact that we're performing MIS on this sample. That's never a good idea. Make sure your laboratory knows up front when these samples are coming and how you need them processed. And keep in mind too that samples are larger than 2 kilograms, they may incur an additional preparation charge depending on the size and what have you of the laboratory's equipment. So make sure you have a good understanding with the laboratory for cost and sample size. Drawing a bulk MI sample, you're going to take the entire sample, spread it out on a large flat surface. We use baking trays with a piece of foil. The big clumps are broken up with a gloved hand. The entire sheet is weighed and the weight is recorded. The sample sets overnight, and the next morning we weigh the sample again. Now we wait at least an hour after that weight is taken, and we weigh the sample again. If the difference is less than 3%, then it's considered air dry. And this is generally adequate for reporting of contaminant residues on a dry weight basis. And if you don't get the soil dry, grinding and sieving is going to be a problem. There may be situations where all you want to do is incremental sample your wet sample. In this instance, you're going to spread the sample out as evenly as possible on a flat surface, like the baking dish. You're going to break up the clumps as much as you can. Make sure it's as even as you can. And you're going to subsample using the two-dimensional Japanese slab cake method, taking a minimum of 30 increments, all the same size. Now, since this sample is not air dried, you're going to also need to take an incremental sample for the moisture correction. And you can always take a larger mass for the moisture correction also. The larger the mass, the better the reproducibility. You may want to take a wet sample and sieve it and not dry it. In doing that, you're going to pass your entire sample very slowly through your number 10 sieve. You want to be careful not to force things through the sieve. You could damage it. And once again, you don't want anything greater than 2 millimeters. You're going to break the dirt clods up as much as you can and gently push those through the sieve also. Then you're going to incremental sample using a minimum again of 30 increments. And since this sample is not dried, once again, you're going to have to go through the same procedure to do moisture correction. You may want to dry and sieve your sample, but not grind. In order to do this, you're going to go through the drying like we did on the bulk picture we had earlier. The sample is going to be laid out overnight, dried, weighed the next morning. Once it comes to a constant weight, you will put it through a number 10 sieve. And you want to make sure that all the aggregates are broken up either by hand or by mortar and pestle if needed. The only things left on that sieve should be rocks and vegetations. So you want to make sure that the entire sample is processed. Dry weight or moisture corrected results are required for most analyses in most states. If the sample is air dried, this criteria is met. If the sample's not air dried, as I mentioned before, you're going to have to take a separate aliquot to determine your moisture. Here we have a portion of the dried material. Whoops, I skipped a slide. Whoa, I'm missing a slide. Okay, we have a portion of the dried material. It's transferred to the number 10 sieve and sieved onto a clean surface. This is done with a sieve large enough to accommodate your sample. This is a 12-inch sieve that he's using here. The particles that are left on top of the sieve are going to be put into the mortar and pestle, and this is going to be repeated until there are only sticks and gravel left on the screen. This is a critical step. If the entire sample is not processed in this fashion, the efforts of the field can be jeopardized. This is also the place where it's very, very easy to take shortcuts. Manually sieving the sample takes time and effort, and mortar and pestling is a bear. So it's important that the entire sample be processed and not just the easy part. You're going to get tired of hearing this, but it's so important. The most important part of multi-incremental sampling in the laboratory is to ensure that the entire sample is processed. This is the biggest mistake laboratories make. So you should probably ask your laboratory, how can they prove to you that the entire sample is processed? One way to demonstrate this is to take a picture. On the right-hand side, this is a 1-quart Ziploc bag. Those are the rocks and the gravel that would not go through the number 10 sieve and that could not be mortared and pestled to go through the number 10 sieve. The stuff just behind it is the passing fraction that did make it through the number 10 sieve. On the left-hand side, there's a bullet. If we find things on the sieve that are a little bit different and things we're not expecting, we'll actually take a picture of that too and inform the customer. You can also sieve and then grind. Sieving, if you're going to grind, most of the time, 99% of the time, if you're going to grind, the sample has been dried. So you're going to mortar and pestle and get all of that material through the number 10 sieve. And remember that mortar and pestling is not mechanical grinding. And not all grinders are created equal. We use the puck mill because it gives us the same size particle. The particle sizes are consistent. This is a LabTech ESSA LM2 ring mill. It's capable of grinding to 75 microns. For samples that may contain nitrocellulose, we typically grind 5 by 60 seconds, but mostly we grind a single 60-second or a 90-second grind, depending on the compounds of interest. If the bowl gets hot during the grind, we'll wait 2 minutes before the next grind. And the grinding times can be adjusted to meet your data quality objectives. It's possible to overgrind a sample too. The soil can re-aggregate and form clumps, and in doing that, your incremental sample is messed up after the fact. And as I mentioned before, the ring and puck mill we use because it grinds the sample to a uniform size. These are the bowls that are used inside the puck mill. They are stainless steel bowls, and we put the soil in the bowl, and the puck is set on top. Then we put the top on it, put it in that grinder. It's important to keep the bowls and pucks identified in case of cross-contamination. The bowl, the ring, and the top are labeled as a unit. And I was hoping you'd be able to see that etched in the steel are the letters identifying each one uniquely. This is a picture of the soil once it's been ground in the puck mill. And it's important to keep the bowls and pucks identified, like I said, in case of cross-contamination. And the units are always used together. The units will wear, and it's important to keep them together so that the wear areas are all the same. And this makes cleaning the units easier. A sample that's ground to 75 microns is about the consistency of flour. That's really kind of cool. After each sample, we grind a sand blank. We'll grind the sample, we'll wash the bowl, we'll dry it thoroughly, and then we'll grind blank sand. We'll do this after every sample. Once the sand is ground, we'll put the next sample in and grind it. And we'll do this for each bowl after each sample. This way we check for cross-contamination. I do have to say though, we've never seen cross-contamination in the bowls. The cleaning process is pretty thorough, and we've had samples that contained up to 2% of TNT with no cross-contamination. The sample mass affects the fundamental error, and it's important to determine how much mass is needed for each method. Hawaii requires a minimum of 5 grams for their mercury analysis and at least 10 grams for their metal analysis. If the sample's ground, this reduces fundamental error, which will reduce the amount of mass needed for each method. A grinding study was conducted by EPA Region 3. They did 24 soils, and those soils were sieved, incremental sampled, tested, then ground, incremental sampled, and tested. And the pre and the post grind results for those metals, they were virtually identical. The only metal that showed a statistically significant post-grind concentration was chromium. That's not surprising at all, because as we said, that contribution is from the bowl. Now the results from this grinding study are pretty consistent with others, so it's notable to point out that there was no increase in the pre and the post grinds for the metal results. One triplicate is recommended per batch, and we talked about one triplicate being done in the field and one triplicate being done in the laboratory. The triplicates must be run on a sample. They can't be run on a blank or on a grinding blank. And it's important to compare the results. If the percent RSD is greater than 20%, then we generally contact the client. We may need at that point to take a larger sample mass, or perhaps if the sample was not ground, perhaps we need to grind it, or if it was grind, perhaps we need to grind it finer. This is a sectorial splitter, and it's considered the most precise way to collect representative subsamples. If you're interested, you can refer to US EPA Lab Subsampling Guidance Section 4 on sectorial splitters. The sectorial splitter reduces operator-technician error associated with sampling by hand. Remember, we have to take 30 increments. They all have to be the same size, and when they're done, they have to add up to the amount of mass we're using for that analysis. So it can be pretty tricky. This sectorial splitter is also the best way to subsample soil that's not been ground, because it reduces the problem of sample particulate size variability. However, using the sectorial splitter, you're most likely going to need to split the samples more than once, in fact, many times, to get it down to the desired amount. If we were looking for 10 grams, it would take quite a while to reduce 1 kilogram of sample to 10 grams. And it also involves more cleaning in between. So while this is technically the best way to do it, it takes way more time, and it's not done very often. Multi-incremental sampling can be used and is used for volatiles also. The laboratory generally provides the containers, and the containers can either be a wide top or a narrow top. These containers have methanol in them. We typically have our samples transported by air, and you can have a maximum of 30 milliliters of methanol per container for air transportation, and a maximum of 1 liter per ice chest or outer container. And the ratio that you use for volatiles is a 1-to-1 ratio of soil to methanol. I'm afraid I don't know what the ground transportation rules are, but those are for air. Mistakes are made when communication is not clear between the lab and the client. Ask as many questions as you wish. It's important to get it right. It's also very important, as you've heard time and time again, that the entire sample be processed, that all the clumps are disaggregated, and that the sub-sampling portion is not rushed. It needs to be consistent across the entire sample. And as stated before, this takes time. Also, if you're going to grind, grinding must take place at the proper time. And this needs to be understood by the lab and by the personnel that are doing the grinding in the laboratory. All parties involved need to understand and decide how much sample mass is needed to decrease sampling error to an acceptable level for your project. The amount of time the sample needs to be ground is also important to obtain the desired particle size, and at the same time not losing any of your analytes. If bioaccessibility is evaluated, the proper sieve size will need to be identified, and the proper grinder must be used. And the communication, like I said before, within the laboratory has to be clear. For instance, here, for the metals analysis, there'll be no grinding. So the sample with just the pebbles and sticks sitting out here, prior to grinding, this sample will be laid out and multi-incremental sampled for the metals. Then it's going to be ground and incremental for the volatiles. Now, if the communication wasn't proper, you can't ungrind a sample. So laboratory communication is critical also. Grinding decreases sampling error and makes it possible to use fewer increments and less mass, and it improves precision. There may be some analyte loss due to volatility, and bioavailability must always be done prior to grinding. The reporting requirements need to be understood by the laboratory, and they should include the initial size of the MI sample, the final volume extracted or digested, information on how the sample was prepared and presented in the final report in sufficient detail to understand the entire process for all analytes. You should include all the data from the replicate samples and to include a reference to the laboratory SOP used. Well, your takeaway information, I hope you understand now that there are many, many ways to use MIS in the laboratory. And just be sure whatever course you take, the lab processes the entire sample, that the lab understands what your needs are, and that the lab follows through with incrementally sampling and doing so properly during the laboratory process, that your triplicates are performed at frequencies needed to meet your DQOs. If you need any additional information, I can be reached at that email address. I'd like to thank John for all of his help. He went through my slides many, many times and helped me. Roger, thank you for allowing me to do this and for your guidance along the way. I'd like to thank Chuck Ramsey for answering a ton of my questions and helping me to understand more about sampling errors. I'd like to thank Josh Barber from EPA Region 3 for helping us with, or allowing us to use his data. And then, not on my slide, I'd like to thank Vicki, her IT staff, and Jeremy, my IT staff, and for all your patience.
Say, Diane, this is Roger, so I'll start off with a few questions that we commonly get.
Okay, thank you.
And anyone has any other questions, go ahead and type them into the messaging block, and Iris will go through those. So I'm curious, and I hear this question quite a bit, is what percentage of multi-increment samples processed by your laboratory are from Hawaii versus other states? And are you processing samples from California?
Yes, we are processing samples from California. Hawaii is probably between a third to a half of our samples.
Okay.
So our largest by far.
Then another common question we get, what percentage of your samples are ground, and what's the most common contaminant of concern?
Well, we typically don't grind Hawaii samples, so probably a third of our samples are ground. The common contaminant, we're asked to do probably PAHs and metals most often, and dioxins, metals, dioxins, and PAHs.
I guess for grinding, lead is a contaminant of concern. That's high on the list for grinding samples, or maybe metals in general.
Yes, lead, especially if there's any chance that there's pellets there, lead must be ground.
All right. Another common question we get is, what's the additional cost for sample processing, like a rough range, and is there an additional cost for grinding on top of that? You have to be real specific.
Okay, some sample processing, depending on what it is, we can do wet incremental, we can do wet sieve incremental, we could do dry incremental, we could do dry sieve incremental. So anywhere from, say, an additional $25 up to $110.
Okay. Now I've heard from other people that grinding the samples could be another $50 to $75, something like that per sample. Is that in the right ballpark? Okay.
Yes.
All right, that's all the common questions I can think of right now.
Diane, I have a question for you. This is John in Hilo.
Yes.
Is it common when you do grind samples that you are first analyze the 2 millimeter fraction and report both the 2 millimeter fraction level as well as the ground fraction level?
You know, when we first started doing incremental sampling, we did that a lot. We're not seeing it as much anymore. We didn't see too much of a difference between the two, so and the grinding, we did get better statistical reproducibility, so most everyone in that instance has gone to grinding.
I guess in Hawaii at this moment, we generally want to see both. If you're going to first test the less than 2 millimeter fraction and then grind it.
And we've done a lot of that.
Yeah. That's maybe just for initial screening of the site.
And another question, Diane, is it how common or uncommon is it for you to get over 15 or 20% RSD on your lab triplicates on subsampling?
Well, it truly depends on if the sample was ground or not. If the sample was not ground, we will see it much more often than we will on a ground sample. Recently we had a set of samples where we were 25 to 30%, and in that point we look at what the QSM says, and it says 20%, so we call the customer and say, hey, this is what's happened, and then they'll tell us what they want us to do from there.
So Diane, this is Roger again. How often do you see RSDs over 50%? That's the level where we really start to be more concerned from a risk standpoint. Is that very common?
50%? No, that's not. We don't see them there very often. We're more likely to see them over 50% in a field duplicate than in a field triplicate than in a laboratory triplicate.
Right. So as you said earlier, the largest source of error typically, once you process the samples properly, is going to be in the field again.
Correct.
Okay.
Or that's my understanding. I'm not an expert there.
It is. It's the geologists like me. It's not you. Chemists are doing a great job.
Thank you.
I think I also want to compliment you. I think it's excellent that when you're doing triplicates and you're doing them right, and then you're reporting to your clients when issues come up. It's not common to see that reported at all from laboratories, and I think your emphasis on that today is admirable and very important for people working with labs with multi-increment samples.
Well, we typically do it because the QSM says you should and because it's right, but it is expensive to do. And so, everyone's looking at that, the dollar amount.
Right.
Thank you.
I have a couple of questions here too. One of them from 3 from our audience. One is, do you grind the sift portion or the larger particles or both? So apparently this is still not clear. Can you elaborate on that?
Yeah, I guess I didn't understand the question. Could you try me again, please?
Sorry. Do you grind the sift portion of your samples or the larger particles only or both?
We only grind the sieved. Well, it depends on what you're doing with the MIS. Typically, we grind the sieved portion. The stuff that's left on top, we don't touch again unless the customer asks us to do that.
Okay. Another question is, what type of documentation do you normally include in your data package?
In the data package, we don't put any photographs. The photographs you would have to come back and ask or ask up front to do that. But in the data package, we do include the SOP. We include the initial MIS size, the amount that was used, the triplicate results, and the name of the SOP.
And then the last I have here refers to slide 50. Is this information typically included in the lab report as documentation? Is this provided or part of the requirement? Can you go?
Well, it's, as far as we're concerned, it's part of the requirement. As it says in the method, that's what you're going to do, so we do. We don't always supply it in the final report because our customers don't always want it, but it's there. And we always put the raw data in there so that if they wanted to look, they could find it.
Okay, thank you. That's all I have here.
And John, I apologize, my last slide didn't come up, but you had asked me to include a slide on Chuck Ramsey's next incremental sampling class that he's giving. And it's, I believe, well, it's beginning of February, and it's on his website if anyone's interested.
All right, I did see that slide come up briefly. I'm not sure where it
Yeah,
to, but thanks for that, Diane.
Oh, there it
As
is.
I mentioned earlier, for states or others that are just getting into multi-increment sampling, we've recommended Chuck's training. He has an excellent trainer, and we've recommended his training as sort of the core training element for getting into the multi-increment sampling methodology. So he has another course coming up, and that's what Diane was referring to.
Oh, I found the slide. It's up there now.
All right, thanks very much again, Diane, for your willingness to do this webinar. And this is going to be posted with our other webinar series on DUMIS on our Here Office webinar page, and so you can find it there to review it.
And John, this is Roger. A recording of the presentation will also be posted to our YouTube channel, hopefully in the next week or so. That announcement will be on our webinar webpage. All right, thanks a lot, Diane.
Well, thank you. Bye-bye now.
Bye.
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 Thanks, everyone, for joining in.